now Philippe is here, and I can actually thank him for having me here, for inviting me to speak. I was doing that already last time, but you weren't there. No, it's been a pleasure so far. Yeah, so today I want to talk about codimension 1 cohomology of SLNZ. So that means in particular the goal of today's talk is the theorem of Church and Putman, which says that if you look at the cohomology of SLNZ in codimension 1 with rational coefficients, then this vanishes for n at least I plus. Sorry, I is 1, so 1 plus 2 is 3. So that shall be the goal of today. And I want to point out, first of all, that this result has been used. For example, it can be used to show that K8 of Z is 0, and so this, as Philippe explained, so this is a result by Jutur, Sikaric, Elbaz, Vincent, Coopers, and Martinet, and as Philippe has already explained, we in some sense we know all of the K groups except for the ones where the index is divided by is divisible by 4, I mean, we know K0, we know K4 is due to Rognus, if I remember correctly, and then there is this relatively new result. So let me tell you how we do this. Well, we do this by finding a they do this by finding a presentation, and this presentation was actually first found by Bukovsky, and that's why it's often called the Bukovsky presentation. And so maybe let's first recall what are the so what is, sorry, I'm maybe I should back up a little bit. What am I trying to do? Well, the cohomology by Borel-Serre duality is H1 of SLNZ with coefficients in Steinberg, well, and then taking this rationally. So if we have, I mean, if we want to compute H1, we will need a resolution of this module as SLNZ representations. And it's going to turn out that it's going to be enough to find a presentation to show that it's 0, because in this presentation we will show that the relations part vanishes in coinvariance.
There's quickly implications there. Is that for small n,
this one, yeah.
Yeah.
Yeah. So yeah, for exactly for small small cohomological dimension, Philippe et al. Was computing this on a computer, and now for big dimension, this can be shown using this theorem, that these are vanished, so they don't give you anything extra. All right, so let's see so we want to we want to find a presentation of the Steinberg module. And her lectures was she found generators. So let's recall what were the generators. Generators were apartments. For Steinberg is generated by integral apartments. So what was that? Let's L1 through Ln be a line decomposition of Zn. So now this is an integral frame. Jenny was describing this a little bit differently. She was describing a line decomposition of q to the n, and then saying it's an integral frame if the intersections with z to the n give you a line decomposition of z to the n. I'll just directly go to these lines right here, and then we defined these classes which are the apartment classes, and they generate a Steinberg. Now, from being an apartment class and the way that we defined them, one relation between these. So we want to find all the relations now in Steinberg between these apartment classes, and one relation is quite obvious, namely if you permute the lines around here, you will just, either turn the apartment or maybe flip the orientation. So that means you will get the same class in the end, or minus the class, depending on the sign of the permutation. So that means if I take S off and I apply a permutation onto the lines for pi being as permutation, then I will have to add a sign here depending on the sign of the permutation. So that is one obvious relation. Now there is and now the Bukowski presentation says there is exactly one more relation, not exactly one. I guess this is a family of relation. Is the Manin relation, and that's one apartment. I can write this as the sum of two apartments. Where in this sum, one time I replace L1 with a different line, and one time I replace L2 with a different line. And what is that different line? So let's say where L0 is Z times V0 plus V1 for with Li is equal to, V1 and V2, where Li is equal to the Vi. So what does this mean? I'm saying I take a generator, an integral generator of all of these lines. Now I only have, for each line I have two choices, right? In each line there's only two unimodular vectors, plus and minus itself. And I choose some of these, and then I say I make a new line out of the sum of the two first generators, and I can replace this new line. I replaces L1 in the first summand and L2 in the second summand, and that gives another relation between these. Between these apartments. Maybe let me do a very easy example for n equals 2. If I have the line Z V1 and I have another line Z V2. Now an apartment is just an S0, so it's just 2 points, right? And now I could make a third point like this, and then, well, the difference between this and this is the same as the difference between this and that, minus the difference between these, but well, how does this work now? So this is L1, L2, and L0, and so I'm saying L2 minus L1 is the same thing as L2 minus L0 plus L0 minus L1. Yeah, so that's in this case very easy, and in higher dimensions it's also actually not that hard to see that this is a relation. Bukowski says this is all the relations I need. And then of course you could take, because you permute things around here, you can you could take this to be any of the two vectors you can choose. All right, that was I hope easy enough. Let me go back to some simplicial complexes. And relate that to this. So first of all, so Jenny was talking about the complex of partial bases. I don't quite remember. I don't think she talked. Did she talk about did she mention the complex of partial frames? No. So so this is an integral frame, or a line decomposition, and we could take could take subsets of these. So that means so let's see, Bn of Z we define as the vertices are one-dimensional summands of Z to the n, and then simplices L1, or I think we denoted simplices like this. L0 through LP is a simplex, it's a P simplex. If these lines are linearly independent and they form a summand in Z to the n. So this is a partial line decomposition or partial frame. Yeah. This is very similar to what Jenny said. The only difference is, the only difference is that I don't distinguish between between plus or minus a vector. A line is one vector, except that I don't distinguish between plus or minus that vector. Yeah? Now the lighting changed. Now a partial frame, an augmented frame. So an augmented frame is a set of n plus 1 of z to the n, is a set of n plus 1 lines such that L1 through Ln is a line decomposition. And then we still have L naught. So L naught, again, is, as we just described it here, is equal to this, where the Li's are equal to this. Now again, here's a choice. But maybe I don't want to get into that too much, what the choices are there. But I take all the choices. That's the point. And then I'm defining B augmented to be, again, vertices are one-dimensional summons of z to the n, and simplices are subsets of augmented frames.
Where you write L0 equals, the VI subscript 1, the I subscript, and can be either any two of the.
Here?
Yeah.
So I mean, this is a set, so I can reorder that freely. I just chose an ordering so that I take for L naught these two, and I take L naught to be the one that's the sum. But really, there is some symmetry there that I'm taking into account. Let me draw an example for n equals 2 again, or I can draw the whole space basically. So let's say this is z1 naught. This is z01. Then this will give you a line between them because they form a basis. And so maybe I'll also take 1, 1. Now this will give you a basis. This will give you a basis. And now this gives you an augmented triangle. So this gives you an augmented frame, because this plus this is that. And actually, I can draw all of this into a Poincaré disk. So Poincaré disk is a disk that is a model for the upper half plane for hyperbolic space, and now I'm adding points for each rational point on the boundary, and I get the one skeleton is the so-called fairy graph, and it turns out that there's a lot of triangles, and all of these triangles are exactly the augmented frames. So this would be 1, 2, for example. and so forth. Does this definition make sense? Yeah. All right. So now I have that SL and Z acts on these simplicial complexes by just acting on the lines. Yeah, it just sends a line to a different line, and then but then these conditions of when something is a simplex is equivariant under the action of SL and Z on the lines, and so in particular. I will get that, so I will get that, maybe let's phrase this as an exercise. I will get that Cn of BAN. So it turns out that BAN is an n-dimensional simplicial complex, so I have n-dimensional chains, and let's take this with rational coefficients, and Bn is n minus one dimensional complex. So these chains are they are SL and Z representations. And this exercise is you supposed to show that they are projective. So why is this good? Well, we're going to use these to rephrase Bukowski presentation rephrased. There is I can write this as Q tensor Steinberg Q. Recall, I think this is always kind of confusing, so I just want to recall the Steinberg of Q is a free abelian group. It's not divisible or anything. Even though there's a Q here, the Q just tells me how many free abelian summons I have, and now I make it into a vector space by tensoring it with Q. Yeah, and then I'm claiming that there is a I'm getting too small. Okay, I have enough space here. So I'm claiming there is a presentation like this of projective SL and Z representations. Now the question is, what is this map? I mean, we figured, I guess from Jenny's talk, we know what this map is. We just send so what is in dimension n minus 1, I just have a full frame, and I send that to the corresponding apartment. Yeah, and in her proof, we have actually seen what happens. You take this simplex, you subdivide it. You take a baryocentric subdivision because you consider it as an element in the poset homology of the poset of this simplicial complex, and then you take the boundary of it, and then you get exactly these apartments that we said in the beginning, where it are boundaries of subdivided simplices. Now, so that's that map. But so the new map now is L0 through Ln. Where do we send that? Well, we're going to send this to L1 through Ln minus L0 L2 dot 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 ln and L1 L0 dot 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 ln. So, and now you see this gives us exactly this relation, the Manin relation between the apartments. So this, is that clear? Graham looks a little bit confused. So I have, when I send, this bit is now in the image. So this, I mod out by that. So in particular, that means that the apartment of
You drop the L0 in the first term, you drop the L1 in the second term. What should you drop in the third term?
the L2.
L2, and you switch. Yeah, okay, so it's like
Yeah. Maybe that wasn't completely clear. Thanks. Yes. So we will still need to see that this is an equivariant map. That's not completely clear here at all, but this will actually come out sort of automatically. So, how do we prove that the codimension 1 cohomology is 0 now? Well, what we're going to do is, so it's enough to prove that the coinvariance, so to compute cohomology or homology of this, you will extend this projective resolution partial to an actual full partial, so a full projective resolution. And then you apply coinvariance of SL and Z. And then you get a chain complex, and you want to compute the homology of that chain complex. Now it turns out, it turns out that the covariance of this is 0. So in the chain complex, this is 0. So the homology at this point is 0, no matter how we continue the projective resolution. So what I'm saying is, it is enough to show that the coinvariance of this is 0. And let's see that. We're going to do that similarly to before. In order to see that, we'll take one of these generators and show that they are 0 in coinvariance. So I'm going to take a element G in SL and Z that sends, so let's assume here we have L0 is equal to Z of V1 plus V2, and Li's are Z of Vi, yeah? Then I will take this map that sends V1 to V2, V2 to V1, and all the other let me first say that means that it fixes the sum. Now if I send all of the other VI's just to VI, that would flip this this simplex, because I'm just flipping exactly 2 of the vertices. But this is not an element in SL and Z. It has determinant -1. So easy fix is, I just say this is true for all I between 3 and n-1, and I take the last one and send it to -Vn. That still fixes the line, though. So I'm just, and this is why I need at least n equals 3 here. Yeah, and so this will give me that g of L naught through Ln is equal to L1, sorry, L naught, L2, L1, dot, 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 Ln, which is equal to minus its original. And so that means it's 0 in coinvariance. 0 in coinvariance. At least rationally, or if you invariance, if you allow to divide by 2. Yeah. All right. So having the Bukovsky presentation actually immediately gives this. Now, Bukovsky so we're going to prove, or I'm going to give you an idea of how to prove the Bukovsky presentation. This is again going to be anachronistic. We're going to use the Church and Putman proved the Bukovsky presentation using simplicial complexes. Originally, Bukovsky proved it using algebraic method. Similarly to Ash-Rudolph proved their theorem just with algebraic methods rather than with a simplicial complex method. But yeah, we believe in simplicial complexes, and that they are actually, that you just have to phrase your problem, your algebraic problem, in terms of simplicial complexes. You put your generators in one degree, and then you put your relations in the next degree, and so forth. And that's also the theme sort of Voronoi complexes and so forth. So that fits in quite well. And so this is what I'm going to present. So I want to now go on with the proof of the Bukovsky presentation. And it's going to maybe take a moment. The big thing that we're going to use here is that we will use that BAN is n minus 1 connected. This is hard to prove, or quite technical. So Jenny showed you that Bn is n minus 2 connected. So this thing has 1 dimension more, and it's also 1 dimension more connected. The idea of the proof is quite similar. You're gonna try to take all your vertices and reduce the last coordinate so that you can press it into to the star of one single line, namely the one generated by En. But now you'll have some complications here because mostly because the retraction of that link to the link smaller than there's some stuff happening there. It's not quite as easy. So, but we will just use this. I don't want to go through that proof. I rather want to show you how you have in the exercises a couple of different proofs of how to show something is highly connected. This is just very technical in the end. So we use this, and then let's define one more complex, namely let BA prime be the subcomplex of BAN Z of simplices, let's say L0 through LP, such that, is this still visible? Yeah, it's still visible, okay. Such that the sum of these, now I'm just going to write it like it's not necessarily a direct sum because there's this augmentation that's linearly dependent, but I don't really care so much. So whatever they span is actually smaller than, like it's inside of Zn, but I don't allow that this is going to be all of it. So no full frames and no full augmented frames, only partial stuff, properly partial stuff, yeah? This is what I'm defining here. And then I'm interested in the relative homology between these two complexes. So let me look at the chains of this first. So the relative chains, so I have Ci of BA NZ relative to BI prime NZ, and I'm going to make a distinction between I is n is n minus 1, and I is not n or n minus 1. Okay. What happens when I is n? We're in dimension n. In dimension n, in BAN, we only have augmented frames. Yeah, dimension n means you have n plus 1 many vertices. So the only thing you can have is you have a frame, a full frame, full line decomposition, plus the augmentation. Now that's the only thing you can have, but that certainly spans Zn. So none of that is in BA prime. So it actually turns out that in that case, we just get Cn of BAN. C. For n minus 1, there are two different types you can get. You can either get a full frame, a line decomposition, because that's n vertices, and so that spans an n minus 1 simplex. That is something that does span all of Zn. So that must be in here. But then I also have an augmented partial frame. So I take n minus 1 many lines that build a partial frame, and then I augment that with an L0. That does not span all of Zn, so that would be in a BA prime and gets modded out, gets deleted. So here I only have frames, right? And then if I go in that, if dimension higher than n, there's nothing because this is just an n-dimensional simplicial complex. If I go in dimensions lower, now automatically I don't have enough vectors to span Z to the n. I only have n minus 2 vectors at most, n minus 1 vectors at most. It doesn't span Z to the n. So all of these things will automatically be in BA prime, so the chains there are 0. That means the complete chain complex, the complete relative chain complex is just concentrated in 2 terms, and all I have to do is find a kernel and the co-kernel of one map. So I have the differential now, is I'm going from Cn B, A, N, Z to Cn minus 1 B, N, Z, right? That's the only differential I have. And if I start here with an augmented frame, where do I send this? Well, in BAN, I'm just taking an alternating sum of forgetting certain lines, right? So so let me assume here again that I just want to write this to be precise, and that this is equal to this, and these are these. So what I do is I forget, I can forget the first line, and then I take minus, I forget the second line, and then I take plus, and I forget the third line, which is, the third line is L2. And now I actually am done already, because if I take, if I forget another line later on, then for I bigger than 2, yeah, if I don't forget one of L0, L1, or L2, then the span of all of these lines is not Z to the n anymore. It's not a frame anymore, because you have this augmentations between L0, L1, and L2 that you still have in here. So this would be in BA prime, or so that gets modded out here. And now if I compare this to this map here, I find this is the same, this is the same. Here's a minus sign, here's a plus sign, but here L1 and L0 are swapped. So if you swap that, it's the same element, just a minus sign. So this is exactly the same map. This map comes from a relative chain complex on these simplicial complexes that have the SLN action. So these differentials and the inclusion is equivariant. So that means that all of these differentials are equivariant. And so we accidentally proved that this map is equivariant. Yeah, this is where this map comes from. And one more thing, we proved that whatever the Bokovsky presentation does describe, I don't know if it, we don't know yet that it describes Steinberg, but whatever it does describe, it describes some kind of homology group, this relative homology group here, that's the co-kernel of this map.
How much of what you just said depends on Z?
Which proof?
Well, on what you just, the derivation.
Nothing depends on Z. This needs Z. Yeah. So this is also all of this. So this derivation here, this is a very standard kind of argument that you also do for Voronoi or for Sharpley. It's a very similar argument that you do here. The main ingredient is that this is highly connected in some sense. There's some other things that come in secretively, but here to show that this is n-1 connected, that's not so easy. And there you you can show this for a field. If you can make an equivalent version for fields. We've showed this in a different paper. Alexander Coopers, Jeremy Miller, Jenny Wilson, and I proved this for Eisenstein integers and Gaussian integers. This theorem, and then you get the rest out automatically. This part doesn't use Z at all. So we showed that the Bukowski gives a presentation for Hn minus 1 of BANZ rel BA prime NZ. Yeah, that's what we just showed. Because the Bukowski is literally saying Steinberg is the co-kernel of this map, and the co-kernel of this map is this group. So all we need to show Bukowski, all we need to show is that this is Steinberg. Yeah, so it's enough to show. Enough to show. This is the Steinberg module. And this is actually true integrally. We're going to show this integrally. To where do we need rational coefficients? Well, we need rational coefficients in multiple places. We need we need to be divisible by 2 here to show that this is 0 in coinvariance. And we need that these things are projective. So there we need some, I think we only need to divide by 2 and 3 to show that this is projective. As a hint maybe for this, you should consider the stabilizer of a single stabilizer of one of these augmented frames. That's going to be a finite group, and so you just need to divide by the order of the finite group there. And but then the last bit where you also need rational coefficients is for Borel-Serre duality here. That's where you also need rational coefficients. But a lot of these things work integrally. In particular, actually, to show that that this bit is 0, you can prove that integrally. We have that in some paper somewhere for n greater or equal to 6. And somehow that comes out. Anyway, okay, so this is enough to show. So how are we going to do this? This is actually now working quite similarly to Jenny's proof. So first of all, we take this. Maybe I'll take some more space. N minus 1 of BANZ BA prime NZ. I take the boundary map in the long exact sequence of this pair, and I get a map to this bit. Now in this long exact sequence, what do I have before here? I have n minus 1 BANZ. And here we use that this is n minus 1 connected. That means that the n minus first reduced homology is 0. And we use it again here that this is 0. So in particular, that means that this is an isomorphism. Okay? So we reduced it to this, and then we are, well, I'm going to replace BA prime with the subdivision, the barycentric subdivision of this. Yeah, that's also isomorphic. And now I can find a map from this to the Tietz building. How does this map work? Well, every point in here, every vertex in here now is a simplex in this thing before. Every vertex in here is a simplex here. So every vertex in here is some kind of subset of an augmented frame. And I can just send this to the sum of these, because now this is, well, it's definitely not 0, but it's also not everything. And maybe I should multiply this by Q or something, make this actually a rational subspace. This is not all of Qn, because the sum here is not all of Zn. That's the definition of the prime. So this gives me a well-defined map. Oh, this is a map on the vertices. Now, what are the simplices? Well, simplices here are things that are inclusions of simplices. But then if two simplices like this are included in each other, then certainly their span is also, it gives me included or nested subspaces. So that gives me a simplex over here. So maybe I call this the span map. And so this gives me a map. And well, I want to look at the reduced n-2 homology of this, because this is what I have up here, and because this is literally Steinberg, right? So I want to look at this map. And this map is an isomorphism as well. And now I have to decide how I want to talk about this for the last 5 minutes. So let me be vague, okay? So there is a Quillen lemma. There is a Quillen lemma that basically tells you the same thing as Jenny said. So there's a Quillen lemma that says something like Quillen lemma. And I'm going to phrase it directly here. If T n Q is Co-Macaulay of dimension, what is it? It's dimension n-2. And what else do I want? I want that. So let's call this F. This map. I called it span already, but I also call it F. F, the poset fiber of this map. So what does this mean? This means everything. This is everything in here. So those all p's such that L naught dot 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 plus LP is smaller or is inside of a subspace V. V is a proper non-zero subspace of Q to the N. We need that this is I have to do this right. Maybe Co-Macaulay, or I think this is enough to say that this is, well, let me say what this is. What is this? This is just isomorphic to a BA of V, sort of, BA of dimension V of Z. Because I'm taking all those subsets of augmented frames that are inside of V. And so those things, that means I'll take the integral lattice inside of the subspace, and I exactly get the augmented frames of that. And so in particular, this is dimension V minus 1 connected, and dimension V gives me a relation to the height of this element in a Tietz building, and so this will imply that that HI of this map SDBA prime NZ to HI Tietz building of Q is an ISO for I smaller equal to n minus 2. I don't want to phrase this out completely, but these are the conditions, very similar to the conditions that you saw in Jenny's talk, with the caveat that the coset fibers now are one dimension higher connected, because we now have BA as our coset fibers rather than just a partial basis. Anyhow, my time is up. I will probably go a little bit into the into the map of poset spectral sequence that powers these kind of lemmas in my next talk in the afternoon. But I'll end here, and I thank you for your attention.